So this is part 5 of the final exam semester 1 review, and the first question is about isomers. To remind you, an isomer is something that has the same exact chemical formula but a different arrangement of atoms. And the number one mistake that people make is they'll just draw it flipped around. So they'll go carbon, 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 carbon. They'll put their OH off the end, all their H's, and they'll say that this is different from this one. But if I'm to number the carbons, 1, 2, 3, 4, and I start here, 1, 2, 3, 4, you see it's the same exact arrangement. So just because you draw it in a flipped around order or something rotated around a single bond doesn't actually mean that it's a true isomer. But this one, if you look at the backbone, it goes carbon, oxygen, carbon, carbon, carbon. So that would be an isomer. Or you could just bond 3 carbons together, have one going up, and have your OH coming off of that center carbon. You can see that they would all have very different shapes because you've got to remember that oxygen, for example, has a different size than a carbon atom. So even though we write their letters and they look the same in 2 dimensions, what we're actually talking about is different size atoms. For the other one, there's 2 fluorines which both form a single bond, so you can treat them like a hydrogen, although they are going to have a different shape. So you could put both fluorines on one carbon, you could put one fluorine on one end and the other fluorine on the opposite end, or you could put fluorines on the center carbon. There's a lot of other options for drawing different arrangements of the same formula. The octet rule is talking about how every single atom wants to have 8 valence electrons. Take this carbon, for example. It's got 4 valence electrons. That's where that side of the bond came from. And it's sharing the valence electron of the other atom that it's bonded with. So you can see it adds up to 8. The exceptions that we see often are hydrogen, because hydrogen is happy with just 2. When you're drawing molecules and naming their shapes, it's really important to label all of the lone pairs. And let's do a little recap of the total different shapes that there are, that we're talking about at least. There's tetrahedral, pyramidal, there's bent, there's linear, there's trigonal planar, and they all have some different patterns with how many atoms are bonded to the central atom and the number of lone pairs on the central atom. So if you're trying to figure out what shape is surrounding an atom, if there are 4 atoms bonded to it and no lone pairs, that's going to have a tetrahedral shape. Whereas pyramidal, only 3 atoms attached and 1 lone pair. Bent is typically 2 atoms and 2 lone pairs. Linear is 1 or 2 atoms and no lone pairs. And trigonal planar, like pyramidal, has 3 atoms attached but no lone pairs. So we can see how this works out for some of these molecules over here. These 3 carbons all have 4 bonds, so that's 3 tetrahedrals. This oxygen would have a bent shape around it since it has 2 lone pairs and 2 bonds. Even though it looks like it's linear, if this were actually in 3 dimensions, the electrons would repel each other more than this 90 degrees. So the 2 lone pairs would maybe be coming out of the screen at you, while the 2 bonds would be pushed into the screen. And so it would definitely have a bent shape. Let's review a little bit about how to draw these things too. Which one should we pick? Let's pick CH3SF. Start by drawing the letters of the atoms, but not the hydrogens. And if there's a repeat, like there's a couple of oxygens, it's always a good idea to make things symmetrical. In this situation, we don't really have to worry about that. How many dots do you draw around the atom? You have to check the periodic table and see what group number it's in. Like carbon is in group 4A, so it gets 4 dots. Sulfur is in group 6A. It gets 6 dots. Fluorine is in group 7A. So you start at the top and you go around clockwise until you're done. And for fluorine, the 7, you start then by connecting lonely electrons so that everything's bonded at least once. And then since there were 3 hydrogens, I can easily see that I'm going to need 3 hydrogens bonding to that carbon. And then you can see the shapes, 4 things bonded to that carbon, so tetrahedral. And the sulfur has 2 bonds and 2 lone pairs, so that would be a bent shape. Even if you draw it linear, in 3 dimensions, it's still bent. There's more practice in number 58. It's got an example of a trigonal planar, 3 atoms bonded and no lone pairs. Whereas up here, this phosphorus, we had 3 atoms bonded and 1 lone pair. Electronegativity is all about how greedy the elements are. And certain atoms are greedier than others. And what I'm really talking about is when they're sharing electrons in a covalent bond made of nonmetals. Sometimes, like an oxygen, for example, it will steal more than its fair share of the electron cloud. So poor hydrogen is getting its electrons kind of stolen away from them. Not completely, but definitely more than its fair share. So if I were to draw kind of the opposite of this, if there was equal sharing, you might see, an even amount of cloud around all of the atoms. But that's just not how it is. So back to this drawing, a lot of times you'll see arrows pointing to the atom that is greedier. And you can look up the value. It's called the electronegativity value. And oxygen's is 3.44, hydrogen's is 2.1. Whichever one has the higher number, that gets the partial negative charge, and the other atoms get a partial positive. That's because electrons are negative, so if something is stealing some electron cloud, it will have that partial negative charge, versus the hydrogens have those protons in their nucleus that are positive, and now it's kind of like a cloud going over the sun. They're leaving that hydrogen, and so it becomes partially positive now that more of the protons are exposed. So ultimately, this is called a polar molecule because, kind of like a north pole and a south pole, there's a positive end and a negative end. And that makes these molecules really love each other because another oxygen nearby will be attracted. Another water molecule, the hydrogen of one will be attracted to the oxygen of another. So the big difference between a polar and a nonpolar bond is that in a nonpolar bond, there is an equal sharing. So, for example, if I had a carbon bonded to 4 hydrogens, the value for the electronegativity of carbon is 2.55 and hydrogen is 2.1. That's a difference of 0.45 if you subtract. For something to be polar covalent, it's going to have a difference in electronegativity of at least 0.5 and up to 2.1. If it's above 2.1, then you're really talking about an ionic bond, which is not sharing at all. That's when the metal completely gives its electron to the nonmetal because there's such a difference in electronegativity. So polar covalent is nonmetal atoms only that are sharing electrons, versus an ionic bond is a metal and a nonmetal. And then there are situations where you've got nonmetals that are that have that difference less than 0.5, and that just means that there's no partial charges. So there's no tug of war going on here, creating a partial positive and a partial negative. So that is called a non-polar, since it doesn't have the positive end and the negative end. Those molecules are not sticky. They're not attracted to each other, which they're attracted to each other much less, I should say, and that creates different properties. So you're going to have an electronegativity chart on your exam. I forgot to put it in the equations sheet, which I will. And you'll be able to look up the numbers and see, okay, what's the difference between these two? Like this one has a difference of 0.41, so that's less than 0.5. That means that's not going to be a polar bond. It's a tie. Versus a carbon and a hydrogen, actually this one's same thing, difference of 0.45, that's another tie. But here, fluorine is much more electronegative than the carbon, so it will be the one that attracts shared electrons more strongly. Same with the chlorine versus the phosphorus. Finally, in class we did a distillation, and the whole point of doing a distillation is to separate molecules based on their boiling point. So you'll have a flask with a mixture of liquids, and we talked a lot about how this is the process they use with crude oil from the earth. They start heating it, and the thing with the lowest boiling point, the way that our lab worked, will turn into a gas first. So it'll go up this tubing, you'll run it through a cool water area, and then it will condense back into a liquid. So why are some things easier to boil than others? Well, we talked about length of a molecule being a big factor. If you have two non-polar molecules, whichever one is bigger is going to be harder to boil because those molecules have higher intermolecular forces with one another. And it makes sense. Something bigger and heavier is just going to be harder to turn into a gas. So this one would have a lower boiling point compared to this one. Higher boiling point. But there's a lot of things that change as soon as you've got a molecule that has polar bonds. Again, because these are really sticky. So the partial positive end of one molecule will be really attracted to the partial negative of another molecule. So you could predict that if you were doing a distillation between something like CH4 and water, water has a much higher boiling point because of its polarity. So that's really useful for trying to separate liquids because since they all have a different boiling point, they'll come out of this distillation in different fractions. All right. Good luck with the rest of your